Good morning, my dear students. Welcome you again in my Aniruddha tutorials. I am Dr. M. Venkat. In my previous classes, I started locomotion movement. I discussed about the types of movements, types of locomotions, structure of the skeletal muscle, and the structure of a myofibril, myofilaments, motor unit, motor end plate, and the triad systems, etc. In this class, I am going to explain you about the muscle contraction. For the muscle contraction, there is a theory, and the theory is the sliding filament theory. Sliding filament theory. Sliding filament theory. What is that sliding filament theory? Okay, it is proposed by Huxley and Hansen. Huxley and Hansen proposing that sliding filament theory. In this, myofilaments are sliding. Only the thin filament slides over the thick filament. Only the thin filament slides over the thick filament, where the thick filament is always stationary. The thick filament is always stationary. It is not moving or sliding. Thick filaments never slide. Only thin filaments slide over the thick filament. If you see, when the muscle is under rest, the H zone at the center of the A band, okay, this is the M line, a thin fibrous membrane in the M line. During the rest condition, in a resting muscle, the thin filaments extends up to the end of the H zone. I mean, thin filaments, they never present in H zone during the muscle resting stage. Okay, this is the tail of the meromyosin and the neck and head of the meromyosin. This is the meromyosin. I explain you one thing. Meromyosin has two parts. This is the heavy meromyosin, HMM, heavy meromyosin, and the tail forms the light meromyosin, LMM is equals to tail. So, when the muscle is under resting stage, the edges of the thin filament partially overlap the free ends of the thick filament. I repeat again, the edges of the thin filament partially overlap the free ends of the thick filament. Free ends of the thick filament. See this, the edges of the thin filament partially overlap the free ends of the thick filament, and that remained unoverlapped portion remained the unoverlapped portion this is the unoverlapped portion by the thin filaments and the thick filament is called as H zone. Is called as the H zone. So I repeat again. The edges of the thin filament partially overlap the free ends of the thick filament. The remained unoverlapped portion of the A band is called as the H zone. But during the muscle contraction, the thin filaments enters the H zone because they slide over the thick filament. Therefore, the overlapping portion will increase during the muscle contraction. So, how the muscle contraction occurs? That is explained by the sliding filament theory. The steps in the sliding filament theory are as follows. The steps are: 1. The excitation of the muscle. The first step is the excitation of the muscle and how the muscle is excited. Steps in muscle contraction. Step number 1, the excitation of the muscle. Excitation of muscle. First step is the excitation of the muscle. Excitation of the muscle. How the muscle is excited? If you see, this is the sarcolemma. Muscle plasmalemma is the sarcolemma. Sarcolemma is the muscle plasmalemma. When the muscle is under rest, there is a positive ionic charge in the ECF and the negative ionic charge in the sarcoplasm. There is plus outside, negative inside. This condition is called as the polarization. This is the polarization. Polarization also called as the resting potential. The resting potential or the polarization. When this condition is present in the sarcolemma, muscle is always rest, but a motor neuron from the central nervous system, this is a motor neuron from central nervous system stimulating the sarcolemma at the neuromuscular junction. This is the nerve ending synaptic mountains sarcolemma. A motor neuron from the central nervous system stimulating the sarcolemma at the neuromuscular junction. This is neuromuscular junction. The neuromuscular junction can also call as the motor end plate. Motor end plate or neuromuscular junction. You know pretty well that at the tip of the synaptic boutons there are synaptic vesicles. These are synaptic vesicles, and the vesicles are filled with the chemicals or called as the neurotransmitters. when the vesicle bursts, releasing the neurotransmitter at the neuromuscular junction. So these are the receptors for the acetylcholine, the chief neurotransmitter. Therefore, when the neurotransmitter binds to the receptor present in the sarcolemma, ultimately sarcolemma is depolarized. So, where motor neuron from the central nervous system stimulating the sarcolemma at the neuromuscular junction leads to sarcolemma undergoes depolarization. Sarcolemma undergoes depolarization. What does it mean? During the depolarization of the sarcolemma, there is influx of the sodium ions. When the influx of the sodium ions occurs into the sarcoplasm, there is a change in the membrane potential. The plus inside, negative outside. This condition, negative outside plus inside, is called as depolarization. The same depolarization wave is rendering into the triad system. The meaning of triad system I explained in the previous class. If you want to know that, please check it out. And this is the T tubule and these are the terminal cisternae. Therefore, when the sarcolemma undergoes depolarization and that depolarization wave is entering into the triad system, you know pretty well, the terminal cisternae of the triad system are the reservoirs of the calcium ions, but now these calcium ions are releasing into the sarcoplasm. Calcium ions releases into the sarcoplasm. This is the meaning of the excitation of the muscle. I repeat again, a motor neuron from the central nervous system. Stimulating the sarcolemma at the neuromuscular junction. Arrow mark. Sarcolemma undergoes depolarization. Arrow mark. Depolarization renders into the triad system. Arrow mark. Calcium ions are releasing into the sarcoplasm. Arrow mark. And what happens next? This is all about the excitation of the muscle. The next event is the cross-breath cycle in the muscle contraction. What is the meaning of the cross-breath cycle? Cross-breath cycle is nothing but there are some cyclical events which are repeated again and again for the muscle contraction. The second step is cross-breath cycle. In the cross-breath cycle, the first step is the formation of the cross-breath. So I write here the formation of cross-breath. Is the first event in the cross-breath cycle. What is the cross-breath? The calcium ions which are entering into the sarcoplasm, calcium ions reacts with the troponin C of the thin filament. You know, thin filament has 3 units. One is the F-actin, tropomyosin and the troponin. Troponin has 3 subunits, troponin T, troponin C and the troponin I. These calcium ions react with troponin C, forms the complex called as calcium troponin C complex. When the calcium troponin C complexes are formed inside the thin filament, what happens? Look at the diagram. This is the H zone. The center point, the central membrane in the M line in the H zone. And the thick filament contain, this is the tail of the myosin, meromyosin, and the neck, head of meromyosin. Head contain 2 binding sites. This is the active binding site with the F-actin active site. This is the binding site for ATP. So This is the ATP binding site. It is not only the binding site and a binding site A is N site. The same ATP and also ATP is head of the head of this point. Hence, when the complex is formed, so this is the effect. I told during the condition of the muscle. When the muscle condition, effect is only up to its own. For example, this at the center of the band. Z line is the of the, but what is the of calcium troponin thin filament? Of this complex, calcium troponin is in a thin filament. The tropomyosin is lifted up, lifting of troponin and the tropomyosin. So this tropomyosin are lifted up. These troponins are lifted up. The of the actin are before the are absent. The actins are masked. Calcium troponins are formed in the thin filament. Due to that complex, the troponin tropomyosins are shifted up. Ultimately, the active sites of the actin are exposed. So, these are the active sites of the actin. This is the active site, another active site, and one more active site. This is the exposure or unmasking of the active sites of the actin. So, when the unmasking occurs, what is the meaning of a cross bridge? Cross bridge means the entry of the myosin head into the active site of the actin. For that, it needs energy. Even though myosin head is present here and the active site is open, but for this fixation, for this configuration, and for this movement of the head, it needs energy. It needs energy for that movement, and that energy is provided by the hydrolysis of ATP. I repeat again, this is the first conformation of the head of the myosin. During the cross bridge formation, head fixes into the active site of the actin. For that fixing or for that entry, it needs energy, and that energy is provided by the hydrolysis of ATP. Therefore, the reason for the cross bridge formation is hydrolysis of ATP. The reason for the formation of the cross bridge is the hydrolysis of ATP in the presence of one enzyme, and that enzyme is ATPase enzyme. So adenosine triphosphate is destroyed now into adenosine diphosphate and the inorganic phosphate. This is ADP, adenosine diphosphate, as well the pyrophosphate. But the last phosphate of the ATP has the bond energy. So from this bond, energy is released, and that energy is called as the bond energy. With the help of that bond energy, it got by the hydrolysis of ATP and the myosin head fixing into the active site of the actin. See this, I am going to discuss about the cross bridge formation, and this is the one more active site. This is, for example, one more active site. The head of meromyosin enters into the active site of the actin is called as the cross bridge formation. But still, in the head of the ATP, in the head of the meromyosin, both ADP and inorganic phosphates both are present within the head of the meromyosin. Even though there is hydrolysis, but during the cross bridge formation, at the end of the cross bridge formation, but still adenosine diphosphate and inorganic phosphates are still located, they are present inside the head of the meromyosin. This is the formation of the cross bridge. After the formation of the cross bridge, the second cycle is the power stroke. Power stroke can be called as rotation. Rotation can be called as the sliding. What is that sliding? I told you in the beginning of this class, where only thin filaments are sliding over the thick filament. Thick filaments are always stationary, and this sliding of the thin filament is called as sliding. In the rotation means the head when it binds to the active site of the actin. This is the cross bridge, and heads are rotating towards the H zone in such a way the thin filaments are rotated. Thin filaments are entering into the H zone. This is the meaning of rotation. Rotation means head is rotating towards the H zone, and this stroke is called the power stroke because of the muscle contraction occurs in the power stroke. The diagram is as follows. I show you in a diagrammatic way. Power stroke. Yes, it is the H zone, and M line. This is the tail of neuromycin, neck or short arm, where head rotates towards the H zone. This is the rotation of the head. I justified the meaning of rotation. Rotation means his head is rotating towards the H zone. When head rotates, the active sites which are F actin, which is binding to the head of the neuromycin, and that thin filaments are sliding. Thin filaments are sliding over the thick filament, and ultimately they end on. This rotation are power stroke, which are until are as 1. Filament slides over the thin filaments, the thick filament. Rotation or sliding. Second event is one more change comes. You know, center of it there are Z. The particular Z lines is called the sarcomere. Here, when the power Z lines comes near, Z lines are coming near, I band coming. Therefore, when the coming near, the half sarcomere decreases. The length decreases sarcomere. I band shorten. There is a short because the thin filaments are binding to the Z line. When the Z line is coming near, when the Z lines are coming near, automatically the thin filaments which are binding to the Z line also coming. Therefore, I band length is shortening. Length of the sarcomere is decreasing or shortening. Z lines are coming near. Thin filaments are sliding over the thick filament. These are the changes which are seen during the muscle contraction. What are not changing? What are not changing? The things which are remained as it is, not changing, are the length of A band remains as it is. These are not changing. During the muscle contraction, the length of the A band is remaining as it is. And one more, the length of thin filament as well as the thick filament, thin and the thick filaments also retained as it is. There is no change in the length of the thin filament, thick filament. Somebody says that, you may say that thin filaments are extending into the H zone. There might be a shortening of the thin filament. No, there is no shortening of the thin filament because they are entering into the H zone. It is not the shortening. Therefore, my conclusion is the things which are not changing, retained as it is during the power stroke are the length of the A band is retained. The length of the thin filament, thick filaments are retained. The thin filaments are sliding over the thick filament. Z lines are coming near. Length of the sarcomere decreasing. I band length is shortening. And one more is H zone. H zone may decrease or disappear. H zone also disappear. The meaning of H zone disappearing is, in general, when the muscle is under resting stage, what is the meaning of H zone? H zone contain only the thick filaments, but not the thin filaments. But during the power stroke or rotation, there is a entry of thin filament also. There is no meaning of the H zone now. That is why H zone may decrease or disappear. I band decrease or disappear. The thin filaments are sliding over the thick filament. The length of the circle, the Z near, but these are retained remained as length of the A band is length of the thick also remaining as. This is all about the. And next event the reaction is the stroke. What is the reason for the event in the recovery stroke? Recovery stroke. The reason for the recovery stroke binds to neuromyelin. I should say when they be weak, when there is no ATP, bond is strong. When there is ATP bond, when there is no ATP, bond is strong. Look at this diagram at the formation of the cross bridge. When the ATP is hydrolyzed, it is no way called as ATP. When the ATP is absent here, bond between the thin and thick filament is very strong. But now a new ATP binds to the head of the neuromyelin, bond becomes weak. Bond becomes weak. When a new ATP binds to the neuromyelin. This is the H zone and the M line. Okay, the neck, tail, neck, and this is the head of the neuromyelin. Head of the neuromyelin. A new ATP binds here. When the ATP binds, the bond between the actin and myosin is becoming weaker, they are get separated. But still, the thin filaments are present inside the H zone. I repeat, during the muscle relaxation, during the muscle means recovery stroke, during the recovery stroke, still the thin filaments are present inside the H zone, but a new ATP binds here. There is a separation between the thin and thick filaments is called as the recovery stroke. After that recovery, one more the binding, one more power stroke, one more cross bridge, one more power stroke, and another new ATP bind. This is a cyclical event for the muscle contraction. And lastly, the last step in the muscle contraction is the relaxation of the muscle. What is the meaning of muscle relaxation? Relax for the muscle relaxation, not the stimulation. I see it. Motor stops still. Sir, when the nerve sarcolemma again polarized, I mean it is repolarized. When the sarcolemma is repolarized, the calcium troponins complex or complexes are broken or destroyed. When the calcium troponins complexes are broken, leads to the calcium ions, they go back, calcium ions, they go back to the terminal cisternae. Terminal cisternae. When there are no calcium ions with the thin filament, that is why the active sites of the affectin, active sites are closed or masked. When the active sites are masked, leads to Z lines comes to normal. When does the Z lines are coming to normal? During the relaxation of the muscle. Please remember, Z lines are coming to normal only during the muscle relaxation, not during the recovery stroke. So, I tell you the sequential steps in the muscle relaxation. The steps are: 1. Nerve stops the stimulating the sarcolemma. 2. Sarcolemma is repolarized. 3. calcium troponins complexes are destroyed or broken. 4. Calcium ions they go back to the terminal cisternae. 5. The troponin tropomyosin complexes are masking the actin. Muscle relaxation. Two Z lines are when are coming normal. When they are coming to I band re-established. This one is sarcomere is on the change during the power. They normalize relaxation. Therefore, when lines are to not only during the muscle. I tell you about filament theory again during the muscle. Sliding filament proposed and also handsome. In this slide, only thin filament over the but always thick filaments. Steps which are in the muscle contraction. One is the excitation. One step one in the and during the step one excitation. Neuron from the stimulating one. Sarcolemma is the depolarization reacts is 4. Calcium is into the circle 5. Reacts to the troponin forming the complex. C. Actin proteins are shifted. Two sides of effect unmasked. Formation of it. Power stroke or rotation. Recovery stroke after actin myosin and the muscle. The events which in the muscle back a motor happening the stimulation. Sarcolemma is repolarized. Calcium troponins complexes are broken. The calcium ions are they going back to the terminal cisternae. Troponin tropomyocytes are masking the active sites and the Z lines are coming normal. When the Z lines are coming normal, I band length also normalized, edge zone also normalized. Everything will be normalized during the only relaxation of the muscle. I think you understood my class. Thanks for listening to me. Yes, thank you. Welcome back, friends. And in this class, I am going to discuss about the musculoskeletal system, but regarding the muscle fibers. There are two types of the muscle fibers. One are the red muscle fibers and white muscle fibers. Red muscle fibers are red in color. They are white or pale. In color. Red muscle fibers red in color because they have more amount of myoglobin. More myoglobin, the muscle hemoglobin is the myoglobin. The hemoglobin present in the muscle is the myoglobin. White muscle fibers white because they have the less myoglobin. Less myoglobin. They have more number of the mitochondria. And they have less mitochondria. And one more. These are aerobic muscles. These are aerobic muscle fibers. These are anaerobic muscle fibers. But coming to the sarcoplasmic reticulum, should be very careful. In the white muscle fiber, they have more sarcoplasmic reticulum. More sarcoplasmic reticulum. But red muscle fibers have the less sarcoplasmic reticulum. Less sarcoplasmic reticulum and more sarcoplasmic reticulum. White muscle fibers exhibits the short term, very important, very important. Short term and high intensity muscle contraction. High intensity muscle contraction. Very short term and high intensity muscle contraction is exhibited by the white muscle fibers. But corresponding to this statement regarding the red muscle fibers, important, they exhibit long term and low intensity muscle contraction. So these are the very important differences between the red muscle fibers and the white muscle fibers. So if you see, white muscle fibers have less mitochondria, they are aerobic. In aerobic, when these are anaerobic, there is an accumulation of lactic acid. There is accumulation of the lactic acid. When the accumulation of lactic acid occurs in a muscle, leads to fatigue. There is a high chance of fatigue in the white muscle fibers. But when the mitochondria are more, they are aerobic, no chance of the fatigue. For example, cardiac muscles and the visceral muscles. Cardiac and visceral muscles are coming under the red muscle fibers. But whereas, when they are accumulating the lactic acid because of the vigorous exercise, I mean the high intensity muscle contraction, when they are anaerobic, less mitochondria, for example, skeletal muscles. And these are the differences and the examples of the muscle fibers, white and the red muscle fibers. Thank you. And now I am going to discuss about the Cori cycle. Cori cycle. Cori cycle occurs between the skeletal muscle and liver. Occurs between the skeletal muscle and the liver, Cori cycle. What is that? For example, this is the skeletal muscle. This is the skeletal muscle. And this is liver. In the skeletal muscle, the reaction is as follows. Glucose converts into pyruvic acid, two molecules of pyruvic acids. This is general glycolysis. But when the muscle is continuously exercised, in a vigorous exercise, or when the muscle is continuously stimulated, in a continuous stimulation, in this condition, when the muscle is very fast working or vigorous exercise or continuous stimulation, muscle cannot supply sufficient oxygen When there is a deprivation of oxygen or insufficient oxygen in the skeletal muscle, in that condition, muscle respires by the anaerobic respiration. Muscle respires by the anaerobic respiration. In the anaerobic respiration, the byproduct of the anaerobic respiration is the lactic acid. Accumulation of the lactic acid in the skeletal muscle leads to muscle fatigue. Muscle fatigue. So, what is the reason for the muscle fatigue? Because muscle accumulates the lactic acid. It is because muscle respires by the anaerobic respiration. It is because in a vigorous exercise or a continuous stimulation of the muscle unable to supply the sufficient amount of oxygen. No oxygen, anaerobic respiration, accumulation of lactic acid leads to muscle fatigue. But that can be rejuvenated. How? The lactic acid from the skeletal muscle goes to liver via circulation. Via blood from skeletal muscle to the liver. What happens inside the liver? In the liver, the two molecules of lactic acid, La, lactic acid, converts into two molecules of pyruvates or pyruvic acid, and that pyruvic acid converts into glucose. So this is the synthesis of glucose in the liver, but not from a carbohydrate. Other than carbohydrate, this reaction is called as gluconeogenesis. This reaction is the gluconeogenesis. I repeat again. Lactic acid which is produced in the skeletal muscle, leads to the muscle fatigue, but via circulation, these lactic acids are supplied to the liver to rejuvenate, re-establish the skeletal muscle. After some time, skeletal muscle can be becoming into normalcy because the lactic acids are pumped to the liver. Inside the liver, the chemical reaction is as follows. Lactic acid is then converted into pyruvate. Pyruvic acids are converted to glucose. Therefore, the synthesis of glucose other than a carbohydrate. Pyruvic acid is not the carbohydrate, it is not a carbohydrate. So, other than the carbohydrate, glucose synthesis is the gluconeogenesis, and that glucose via circulation again enters into the skeletal muscle for its working. Via circulation enters into skeletal muscle for the needful. Glucose is very needful for the muscle contraction. So that even though there is a muscle fatigue in the skeletal muscle, that can be re-established, that can be rejuvenated, becomes normal because the lactic acid from the skeletal muscle goes to the liver, then it becomes normal. But in the liver, lactic acid converts into pyruvate, pyruvate into glucose, and this reaction is gluconeogenesis. But via circulation, the glucose is supplied to the skeletal muscle, and this cycle between the skeletal muscle and the liver is called as Cori cycle. It's all about the Cori cycle and the muscle fibers. Thank you very much.